And welcome back to CS224D. Today I will basically wrap up word vectors. I realized from various great questions that you've asked that we went over some details, but obviously there's still a lot of other things missing. So sorry if you thought, oh my god, now do I have to finish the problem set just from what I heard last lecture. There will be more details. So also thanks for all your Piazza and Reddit questions. I don't personally answer them, but I usually look over them and try to incorporate that knowledge or those questions into the lecture. All right, so are there any organizational questions around the class and the problem set or any such things? No? All right, so let's start with a refresher on the simplest first model that you will implement and that will be the basis for a lot of other downstream tasks. So we basically covered the word-to-vec model, in particular the skipgram model. And just to refresh, we had the following equations here. So we have basically the log probability that we want to maximize for a certain center word, and conditioned on that center word t in a specific window, we wanted to predict the words around that window. And in particular, our cost function, our probability had this formulation where we had basically an inner product of the center vector transposed with the outer vectors. And outer vectors had this prime here because they're basically every word was represented in terms of two vectors. Once when we try to have it when we have it in the center, and once when we try to predict a word around that center. And during the class, we basically derived in all the details the gradients for the internal vectors VWI, or we called them VC on the board. But of course, and sorry for not mentioning that earlier, of course we have to calculate all the gradients of all the vectors at in any window. So while we just went through the gradients for each center vector, we also of course need the gradients for all the external or the outside vectors, v prime or u on the board in the equations that we wrote. So basically that will be an exercise for you to try to derive those equations. It's a very similar process, and it'll get you started on derivations of these kinds of models. Generally, in each window, we will basically compute the updates for all the parameters that are being used in that window. And that will be true for all the models going forward. When we have a specific set, when we use a specific set of weights, we'll basically update those weights during training. So let's look at the example here. If I have the sentence I like learning, and my C was only 1, so I only look at one word to the left and one word to the right that I try to predict, then basically in that first window we'll compute the gradients for the internal vector v for like, and the external vectors for v prime I and v prime learning. What would be the next windows, the next word vectors that we would update in that sentence, going one to the left and including the sentence period? Say again?
Like learning period?
Yeah, so v prime like and v prime period and v learning. Exactly. Okay. Are there any questions about that? Mm-hmm.
Is this the last sentence in you, or will you go?
That's a good question. So is this the last window that you would do, or would you go one further? In fact, so far in the lecture, I haven't gone through that, but it is actually a good detail. If you have often very short sentences instead of very long documents, you would like to ideally train on the very first word and the very last word too. So what we would often do is we would actually pad the sentences, and we have like a start token, and we have the words, and then we have an end token of the sentence, and that way that token will get its own vector, that will get its own vector, and it'll be an inside and outside version of that, and then we can basically train on all the vectors. It's a great question. All right, so basically, we have to compute the vectors, the vector gradients for all the different vectors that appear in our data set. And so what I also kind of skimmed over last time was that we have this, our cost function entirely we will call j of theta. And this theta is essentially a concatenation of all the parameters in our model. And in our case, where we only have word vectors, there are no other matrices yet, we will basically just concatenate all these d by 1 vectors into one gigantic 2d times v vector. And v is the size of our vocabulary. So when we basically went through all the derivations to derive these gradients, of course, once we've actually computed them, we want to make an update step. And we went over that very quickly too. So now we'll go over a little bit more in detail how to actually update the vectors. So to minimize this function overall over the full batch, so the entire training data, would require us to basically compute the gradients for all the different windows that we have, and then basically sum them all up. And that would then result in the updates for each of the elements of our vector theta. That now includes as its sub-elements all the vectors of the words. And so the way we do this update is basically for every jth element of that general vector, we compute the new version of that by taking the old version minus alpha. This is our step size, and then taking a step in that direction. And in matrix notation, which we'll use moving forward in the class a lot more, we can write this also this way, or the most common way is down here. So we have this nabla here, the gradient of the function j with respect to theta. Okay, so what would that look like in code? Basically, and this is the most vanilla version of this, it'll be more complicated. We'll eventually have a maximum number of iterations, and there are lots of other clever things we can do. But the simplest way to update these vectors is by basically computing the gradients of the function j with respect to theta. Basically implement this function, evaluate the gradient here. We have a specific abstract function j for a specific corpus here, and our current estimates of theta. And then we basically update theta with this simple line. And something along exactly that line you would probably want to see in your first problem set. Okay, so just to give you an intuition of what happens here when we do very simple gradient descent, imagine you had some kind of cost function that may look like this. So these are sort of the level sets of the function. And you start with your theta parameters in some random space. So let's assume you only had 2 word vectors, and each word vector is just a single number. So sort of the simplest case to give you an intuition, we initialize the first vector v1 as this, and let's assume there's only v2, there are no primes. So obviously this is in much higher dimensional space. So what we then do is we compute the gradient, and then we go in the opposite direction of it and basically try to minimize here our function until we hit some optimum. And this, so these are the level sets. You can kind of expect this to look like a bowl here, and we keep going closer to the center. And now the step size function here is of course very important. If your step size was too large, you might overshoot, end up somewhere here, and that would be suboptimal. And of course this is going to be just a very, very simplified intuition of what's actually going on, because our functions, including this one, will actually be not so nice and in a bowl shape. They won't be convex functions. In fact, if you wanted to look at the side view of a function like this, they will often look more like something like this. And so all we can ever hope for with our models, and we'll go over those things in a lot more details in another class where we look at more advanced things other than just gradient descent, you will always only get stuck in a local optimum. You can't really provably get into a global optimum of your functions, but it turns out for all these kinds of models that will be good enough. Okay, so basically all we're trying to do here is go down and try to minimize this function. So of course, when we try to go over all the windows and compute all the gradients for the entire function j, so remember J here was the sum over all the time steps and then all the windows at each time step. Just evaluating that function would take a very long time. Eventually, our corpus will be something like 40 billion tokens. And depending on how large your window size is, that could be hundreds of billions of windows that we'd have to evaluate. So it would take a super long time before we can make a single update step. That turns out to be a very bad idea for pretty much all models that we'll look at in this class. In all these cases, what we'll instead want to do is to basically update the parameters at each window right away. Because then the next update will be a little better than making an update from purely random word vectors. And this is what we'll call stochastic gradient descent. We'll basically take, and we'll write this here as JT, so it's just a tth window for the cost function J. And in code, this will look something like this. We'll take a window by basically sampling one from our full corpus, and then we'll evaluate the gradient only on that window, and then make an update step right away. Are there any questions about this? All right. So that will basically lead us to a much sparser update vector here. So in each window, we'll actually at most have 2c-1 words, right? We ignore the one in the middle, and we update the outside v words. Well, I guess, and then we also update the one in the middle. So it's actually 2c plus 1. And so basically, our gradients here of jt with respect to theta will be very, very sparse, right? Most words will not appear. We usually have around 1 million words for a large corpus. Most of those words will not appear in a specific window. And so this will be more like what our updates will look like. So for the very first window that we looked at, where we had the sentence I like learning, and we looked at the window with the center of like, and we updated basically the v primes of I and learning, basically this will be a very, very large, very sparse vector. And of course now, if you wanted to compute a lot of those and you add a lot of zeros that really don't do anything for you, it's a very costly thing to do. So in practice, what you will actually want to do is either keep a hash for all your word vectors, and you look up a hash and you basically have your gradients inside a hash, or you will have a sparse update where if you have your L and your L prime matrix, so the lookup tables that include all the different vectors, you'll only update one vector at a time. And especially eventually, and we'll get to that during the later parts of the class, if you have really, really large models and you want to have one computer compute your gradients for one of the windows and another one for another window and so on, you don't want to have to send around that entire large theta vector between all the different machines. Can you raise your hand if all of this makes sense so far? All right, awesome. All right, great. So basically, in the problem set, we'll actually approximate this function, because not only would it be suboptimal to go over all the windows before making a single update step, but it's also computationally way too expensive to compute the normalization factor here. So you'd have to sum over the entire vocabulary, and even that, it's not a sum over billions of things, but it's a sum over millions of word vectors. So basically, you will instead implement the skipgram model with what we'll call negative sampling. The main idea here is, instead of trying to predict the outside word as the probability over all possible words, we'll basically just train a binary logistic regression for a true pair, a center word and a word that really appears in its context, and a couple of random pairs. So the center word with a couple of random words. So in the original paper, and basically one of the goals of this class for me is to allow you to eventually go out into the real world and read papers that people at various organizations publish and read those by yourselves and be able to then take those ideas and implement them. And so I'll sometimes throw out the equations, but then in the next slide I'll actually simplify it a little bit to make it more clear. But basically the full objective function that you will implement in your problem set is the following here. So again, we want to maximize this. So if you want to have gradient descent eventually, you'll just put a minus in front of this. And here we'll have the sigmoid function of the same inner product that we've had before. And so what does the sigmoid function do? It basically maps any number to be between 0 and 1. And we'll actually become very good friends with the sigmoid function. We'll use it a lot throughout this class. So without going into too many details here, you can kind of assume or interpret this result of the sigmoid function as a probability. So what we want to maximize here is the probability that these two words really co-occur together, and that we'll compute the inner product here and then maximize the log probability. Again, the log doesn't change the optimization of this function, or doesn't change the argmax. And so, yeah, basically here in the first part, we maximize the probability of those two words co-occurring. And now to look at the second part, we'll have a slightly cleaner or clearer notation here. Basically, we want to maximize the probability that real outside words appear here, and also minimize the probability that random words appear around the center word. And so here we have the minus, and maybe one thing that you can try to prove at home is that the sigmoid of minus x is the same as 1 minus the sigmoid of x. It's a good exercise to do at home. And so basically what we're trying to optimize in the second part is 1 minus the probability that those appear. So we basically discourage the model from predicting that a certain word that is random would appear next to that word. Again, the assumption here is that if I have a sentence like I like learning, and then I replace one of the words with a completely random word, like I like projectors or something, maybe that's less likely, or I like crying or something like that, some really unlikely word that's basically random, then the probability of that should be smaller. Okay, and so we'll sample these random words based on this probability distribution here, Pn, which will essentially just be the unigram counts divided by the total number, and then each of these unigram distributions will raise to 3/4, and that is a little bit of a hacky thing, and the authors in the paper don't really give a principled mathematical reason for why it's 3/4 other than it worked well in practice. But intuitively what that does is when you have very small numbers and they're raised to the power of 3/4, they'll become a little larger, so you're more likely to sample less frequent words when you use this distribution. Okay, so high level again, intuitively here, we want to maximize the probability of these two words co-occurring, and we want to minimize the, again, binary distribution here, binary probability of these two words not co-occurring. All right, inside the problem set, we also mentioned a continuous bag of words model. Turns out we'll make the problem set a little easier. I think you'll have enough to implement and digest already. So the implementation for the continuous bag of words model is not required, but you can do it for bonus points. The main idea here is it's actually very similar, in some ways an interesting corollary to an interesting sort of opposite model, which is instead of trying to take the center word and predicting the outside words, you'll take the sum of the outside words and try to predict the center word. Essentially, both will capture co-occurrence statistics in the end, but sometimes one works actually better for some tasks than others. All right, so what do we actually do in the end with those two sets of vectors? In the end, all our downstream models will just want to have one vector for each word, not this one that was an outside word in this model, and so on. And so basically what we end up doing, and what seems to work best in practice, is to just simply sum up the two word vectors. So we have two large matrices of all the different word vectors when they were center words, one another large matrix for all the words when they were outside words, but really that distinction is arbitrary, right? As you move one to the left, what used to be an outside word is now an inside word. And in the end, both roughly capture these co-occurrence statistics. And so we'll basically just sum them up. That will be the default. This is actually one of the many options or hyperparameters, so to say, that was first explored explored very well in a paper by Jeffrey Pennington, the global vectors for word representation. And so yeah, another option would have been we could just concatenate the two. So instead of, you learn two sets of d-dimensional vectors and then you end up with a 2D dimensional vector for every word. There are different options, and I encourage you in your problem sets also to play around with these and try to gain some intuition of what works best in what cases. All right, so now we've computed all these vectors, and I've hinted at the fact last time that they capture all these interesting analogies. But ideally, when you run any machine learning experiment, and certainly any deep learning experiment, you want to have some number in the end that tells you whether you're doing well or not. You don't want to have to just look at a couple of examples and see, oh, because these two words are similar, hopefully this was better, but then you miss a couple of others. So ideally, you will evaluate your word vectors in some principled way. And this actually leads me to a brief detour on how to evaluate natural language processing and really any kind of machine learning models in general. And there, in many cases, and for many of the projects that you'll have two kinds of options: intrinsic versus extrinsic evaluations. Intrinsic evaluations are often for specific or intermediate subtask. In our case, for instance, the analogies. They're often very fast to compute, and they help us to understand that specific subsystem that we're training and trying to optimize. However, in the end, you don't usually care about just learning word vectors for their own sake, right? You learn word vectors in order to then solve a harder task, like machine translation or question answering or so on. So the problem with these intrinsic valuations is that it's not always clear if they're really helpful. Like, let's say I optimize these word analogies really well, and then I try to run a machine translation system, and even though I just showed that my new word vector model has a 5% improvement in word analogies, it now works 2% worse in machine translation. And there's no clear definition that the intrinsic evaluation and improving these intrinsic measures will help on downstream tasks. So ideally, whenever you do that in practice, you will actually try to develop or compute some positive correlation that when you improve something in your intrinsic task, there's actually also an improvement in a real task downstream. On the other hand, the problem if you just evaluate on the extrinsic tasks right away is that it takes a very long time. So, let's say you improved your word vectors, you just tuned one hyperparameter a little bit. Now you just want to really quickly know if that helps or not. Now you have to train this whole other machine translation system on top of them. So that will slow down your development time, and that's really suboptimal. In general, in most of your problems, both in practice and also for your problem sets, you're going to want to try to have a very fast iteration. I have a new idea, I implement it, and a couple minutes later, or most half an hour or so for all the kinds of models that we're working on in the class, you want to see if that worked or not. So it takes a very long time to really improve or see if you can improve an extrinsic real task. And it's also often unclear if the subsystem that you're developing is the actual problem or it's actually the interaction with other subsystems. So maybe in machine translation, you may have different components. One learns the word vectors, another one learns how to do something else. So now when you change your word vectors, maybe the rest of the model needs actually to also be changed. So again, it slows you down your development. However, if you did this, and in the end, the proof is sort of in the pudding of a real task. So if replacing your subsystem you're replacing an old subsystem with your new one, and you actually improve the overall accuracy on a real task, then you're set. Then you showed that, for example, your word vectors are very useful. All right, so let's look at a couple of examples of real, intrinsic word vector evaluation tasks. So what we started talking about, and we'll go over a little bit more in detail today, is these word vector analogies. So I want to, when I say man to woman is like king to what? So basically, the way we'll do this is that we'll evaluate word vectors by how well their cosine distance after addition of various other vectors in the analogy capture semantic and syntactic analogy questions. And one interesting side note here is that all the people who run these experiments actually discard the input words. So if you take man to woman is like king to, you don't allow the model to ask to also give king as an answer. And this actually makes it slightly less exciting because oftentimes, if you actually let that happen, it might just say king instead of queen, for instance. So that is sort of one important side note. And another problem before we go into this, because it is really amazing that it happens, but one thing that I want you to understand is that maybe the information was in the word vectors here. If you trained another word vector model and now it doesn't do well on this specific task. But maybe these kinds of analogy, the kinds of semantic information, syntactic information is still in these word vectors, but they're not linear. They're not, this vector plus that vector minus this other one, but they're, you pipe them through some complex nonlinear function, neural network kinds of functions that we'll go through later in the class. So just because you don't do well on this doesn't necessarily mean your word vectors don't have this information in them. But of course, if it is in there and it's very linear, that's very nice. All right, so basically, here's again just the cosine distance. So intuitively, we would like to have things like king minus man plus woman goes to something. So we have here king minus man plus woman, and then we compute the cosine distance to a bunch of different vectors wx. And that distance, ideally, will take the maximum, the vector, the word x, such that that cosine distance is maximized. It's minimized. Sorry, maximized. All right. So basically, just to give you an idea of what we're really, when we say, all right, this works in 70% of the cases, what does this data set actually look like? So here we have syntactic and semantic examples from the original data set. And here are first couple of examples for semantics. So here we have city in state. So if we say like, Chicago to Illinois is like Houston to what other state? And yeah, this is basically one of the sets of analogies that we're trying to do. And there are basically a lot of them. Of course, if you know a little bit about geography, you'll know that some cities actually appear in, have this, different cities may have the same name and appear in different states. And this will not be captured. Basically, if your corpus talks more about the right one here, then you're in luck. So it's just a caveat of this subset of the analogy questions. Another one is a capital and basically some capital in somewhere in the world. So here, again, one problem might be that you look at an older corpus and maybe the capital will change. But in general, if you have the right kind of corpus, like Wikipedia, you would assume that the capital appears more often, the current capital appears more often in those articles than some ancient or previous one. All right, so those were two examples of syntactic, specific tasks in this data set. Another one here, another next two are syntactic. So we basically have, bad to worst is like big to what? In this case, biggest. And there are, again, a lot of examples that you're trying to capture with these linear systems and cosine distance. And the last one is different past tense of verbs. So you have dancing to dance is like feeding to what? All right, so here's a first table that shows you how often you can get these right with various different models. We have here the standard model that we described in the very beginning, like singular value decomposition based models, SVD. There are lots of different kinds of tweaks that you can do to SVD to actually improve its performance a lot. We have here the skipgram model that you'll implement in your class and the continuous bag of words model. And one thing that you'll immediately observe here is that smaller word vectors for these kinds of tasks don't work as well as often higher dimensional word vectors. However, it's not always the case that the highest dimensional word vectors work the best. One thing that is clear is that if you actually have a larger corpus, so this here is the corpus size in terms of tokens, so you have here 6 billion tokens, then the larger your corpus is, the better, right? Which is kind of intuitive. If you have a very small corpus, you might not have the capital of Nigeria even being mentioned in that corpus, so you won't be able to get that analogy question right. Or maybe it's only mentioned once in a really odd corpus, like just some famous actor visited some city, and then again, you won't have a chance to capture that this is actually the capital. In this case here, the glove vectors that we briefly mentioned before work the best, but there are actually a lot of connections to these. So in order to understand this evaluation a little better and also give you an idea of how important it is to tune your hyperparameters and gain intuition for them, here are some plots from the original glove vector that basically analyze various decision points that you can make when you implement your word vectors. So the first one here is the vector dimensionality. And basically they look at syntactic accuracy, semantic accuracy, and the overall accuracy in this analogy task. And basically what we observe is that after 300 dimensions, the overall accuracy, barely goes up further. But until then, it really improves significantly. So if you're ever in a plot and you plot, and this is going to be potentially important for your next couple of problem sets throughout the class and definitely for your final project, if I ever see a plot where you basically have some kind of hyperparameter here and some kind of accuracy that you want to maximize, and the plot looks like something like this, and then you end there and you say, all right, I'm done. The deadline came up and I started the project too late and now I can't run more experiments. Then I would probably subtract some points because I would like to see whether if you had just run another hyperparameter that is even larger, it would have gone up further, or if it actually went down from there and you found the optimal right here. So this is kind of what happened here. Oftentimes, for these kinds of models, eventually there will be a slight drop-off. So one hyperparameter that the glove model and the skipgram model have in common is the window size. So how many words to the left and how many words to the right do you try to predict from the center word? And here we again observe that roughly for the overall numbers, around 8 or so, that basically plateaus. And then for more, you don't really gain something, but of course it's a lot slower, so you'd prefer to use the smaller window size. And this one is interesting too. Here we have an asymmetric context. So far we've only talked about predicting the left C words and the right C words, but it turns out you could also just predict the last couple of words. And that is the asymmetric context, and you can see here that basically just using the left side and predicting left side does not work as well as predicting left and right. Okay, so this is again the intrinsic evaluation. So in some sense we have some idea here. Hopefully these kinds of vectors work well, but of course it's impossible to say for sure until we run them also through some extrinsic tasks. Here's another interesting analysis that basically shows us that training longer helps. And it seems kind of trivial, but I myself had a project in my PhD where I came up with a new model. I thought, oh man, this model is so exciting, it's going to be a great paper, and then I didn't have the right, I didn't get great accuracies. And I fiddled around with a lot of different options, and at some point I just tried to just let it run a little longer, and it turned out that was all I needed. So I was somewhere in this regime here, and I really needed a couple of extra percent for this model to become the state-of-the-art model. So it's very important to plot your accuracies over time as you go through more and more windows in this case, but later on through more and more data samples in general, and write this plot down and show basically, okay, my function has converged, I'm not getting any more improvements as I run this over time. And there will be lots of tricks like that. We'll actually have a special lecture where we'll cover a lot of tips and tricks for making neural network models work. All right, and lastly, this is sort of the most important one, and actually an important lesson for all of deep learning models. More data helps, always. If you have two data sets that are roughly the same size, then the quality matters. So in here, in this case, we'll see the overall accuracy in red, and if you train that on Wikipedia versus GigaWord, which is a corpus based on news text, then Wikipedia, even with 1.6 billion tokens, covers a lot more, different kinds of topics, really tries to have clean language. It's not just about the same kinds of news sources or news topics over and over again, but in general, even just combining these two to have an even larger corpus will be better than either one of those. So even though this corpus right here actually didn't work as well as this, together they still do better. And this is an unfortunate truth for deep learning because you're trying to have a model learn all these things that, in other machine learning models, you might give it by hand, right? You might, by hand, say stronger and strongest is like strongest is the superlative of strong, or that this city is, the capital of that country. Right? You could give a machine learning system a lot of information by hand, but you're asking here a model to learn all this by itself. In order to actually be able to do that, you have to also give it sufficient data to train it. And that will lead, sometimes this is a little disillusioning in the sense that you get into the field of machine learning, you say, oh, I want to just implement the coolest new models, and then you spend a lot of time speeding up your code and trying to distribute your code and so on. And we'll cover that in the class too, on how to try to implement these models both quickly in terms of your own development time, but also such that they run very quickly in the end. And in some cases, maybe you even have to implement them on a GPU to use the potentially 5,000 cores that a single GPU might have. But in general, for just getting a sense of how these models work, we can get away with Python in the class. If you want to do really, really well and train a very large model, you may want to use like Python or something for your final project. All right. Are there any questions about the analogy tasks and the evaluation? All right. Moving on to one other very commonly used intrinsic evaluation metric, and the last one that we'll talk about today, is basically looking at whether word vector distances have high correlation with human judgments. So what do I mean by that? You could ask maybe 5 or 10 people, ideally at least 3, how similar do they feel like tiger and cat is on a scale from 1 to 10? Seems a little ridiculous, and it's clearly very fuzzy, and you clearly don't want to do that with just a single person, but you can basically do that for a lot of different words. So computer and internet, on a scale from 1 to 10, how similar do you think they are? Or maybe going all the way down from like stock to Jaguar. How similar are those? And those you would on a scale from 1 to 10, they're maybe close to 0 or just 1. So now you basically ask people that, and then you will just compute all your statistics, and you look at, again, various distance metrics like Euclidean distance or cosine distance, whether your word vectors and their distances correlate well with those human judgments. And if they do, then you claim victory and you say, oh, my vector space kind of captures similar intuitions about semantic and syntactic similarity between words than humans have. So one very commonly used data set for that, from which I've got these examples, is called WordSim 353. So it basically only has 353 word similarities. And it's a very small data set, so it actually has quite high variance. Again, here you can look at different word vector sizes and different methods. WordSim 353 is one of these correlation data sets, and there are a couple of others. And so in this case here, the glove word vectors actually performed the best, but people have now been able to also use some of these ideas, like summing both of the vectors together on the scriptgram to improve the scriptgram models. All right. One side note, because that question came up in, I think, either Reddit or Piazza, what if you have ambiguity? Right? What if you have the word vector for run, and now it can say, I can use the word like we run every day, or I went for a run. Right? So it could be a verb or a noun. And ideally, if you have run and walk, if their nouns have a certain distance, and running and ran has, is also in good correlation or good vector distances with themselves. So basically, one thing you could do is just ignore that and just assume, well, if I use that word vector later on in some other system, ideally that will disambiguate what's going on. And I capture inside the word vector that this could be used both as a verb and a noun. Another option, which we explored with Eric Huang, who's now a PhD student here at Stanford, me and Chris Manning, is basically to improve these word vector representations by having multiple word prototypes. So what we can do is basically concatenate all the word vectors that we have from a first system, and then do that for basically all the words. So let's say we have here the word bank, and now we find all the contexts in which bank is the center word, and then we run a clustering algorithm. This is one of the prerequisites, but I'll just ask really quick, who here is familiar with k-means clustering? Wonderful. So you just run basically k-means on this. You set k to maybe 5 or 10, and then you basically have different clusters for all these vectors in their context, and then you can say, all right, now I will assign, this is bank 1 because this vector here was part of cluster 1, and maybe bank 2, this context, long context vector. Again, we just concatenate all these vectors and run standard k-means. Bank 2 here is in this other one, in this other cluster. And so this is kind of what the result will then be. So here you have bank 2 is actually learned to be sort of the river bank. So it's closest to a plateau and territory and gap. And bank 1 is close to finance and transaction and laundering and so on. So it's basically the other meaning of bank. And Jaguar is a nice example. There's the car, the convertible car. There's some software named Jaguar. I think there's also a base, like an instrument, Jaguar instrument, and then here you have the Jaguar as the animal. So basically, if you wanted to, you could run this kind of model and learn multiple different vectors for the same word. It turns out in practice very few people do that. We actually, in many cases, will just keep one vector around, and we hope that the subsequent models that use these vectors will pick out the right aspects from that vector to solve their task. I mentioned that we have intrinsic and extrinsic evaluations. We can't really fully appreciate yet how these numbers come about because we don't know yet these downstream models. But just to give you an idea, one thing you would assume works well with these vectors is named entity recognition, right? We saw that companies and their CEOs are in specific distances and the specific relationships, and countries and their cities and so on. So just trying to go through a text and classifying whether specific word in that context is a city or a person or an organization is something that should come quite naturally to these vectors. And indeed, that works quite well to use these as features. Here are a couple of different data sets, the Mach and ACE corpora. And basically, these kinds of models work very well. The differences here are actually quite small. So all these different vectors, like continuous bag of words, and work in the 80 or 90% range. Okay, so one of the major benefits that we have is that we can actually basically train subsequent models on these. Basically, we can, like I just said, classify in the simplest case just whether something is a location or a person or so on. And so we can use these vectors to essentially classify different things in the world, different word vectors. Another one is actually that we can incorporate any kind of information into them as well. So instead of just predicting the words to the left and the words to the right, which gives us co-occurrence counts, which capture sort of semantic and syntactic similarities, we could actually also try to predict whether that word is positive or negative. And that leads us to the next big area of the class, which is classification, and in our case, the first and simplest model, which is Softmax, the Softmax classifier. Basically, this is for those of you who have taken like an NLP class, very similar to maximum entropy classification or logistic regression. And for now, we'll do the simplest one, which is just classifying a single word vector. Eventually, of course, we'll classify much more complex things like windows or sentences or whole documents. So let's go through Softmax classification. Just so I can adjust my speed again, could you raise your hand if you're totally familiar with Softmax or logistic regression? All right. 3/4 or so. So let's go over this a little bit. So basically here, what we're trying to classify is with a specific word vector x, and let's assume here that each word vector just has 3 elements. So our dimensionality here, d equals 3, and we just have 2 classes. It turns out for just 2 classes, it doesn't actually matter to use softmax, because we could just use the sigmoid as we did before, because then probability 1 is for one class and 0 is for the other class. But for simplicity here, this is the kind of figure that we would draw for a 2-class softmax classifier for a 3-dimensional word vectors. So we have here in general a matrix W, which has C many rows and D many columns. So we'll have C times D. And what we basically want to optimize, or maybe before we go there, I'll just give you some intuition here. So when I write wy dot, I usually mean that I take the yth row, and basically the entire column here is the dot. So the dot means we'll take the entire column. So if I wanted to get a column of, sorry, the entire row. So if I wanted to get a column here, I would write w dot, and then I for the ith column, and wy dot for the yth row. And so in order to compute here the probability for a specific y, we will take the yth row of that matrix and multiply it by our word vector x. And that will just give us a single number. So this w here. And now, in order to get an actual normalized probability, we will do this for all the different classes. And then, well, first we take the exponent of that, so we have a positive number. And then we'll basically divide that by the normalization constant that sums up the exponents of all the other classes and this class as well. All right, so let's go over the details here. In general, when we have a softmax, we will use as our general loss function, the overall function j that we try to optimize, the cross entropy error. Also, in terms of terminology, we'll often say we have either loss function or cost function or objective function. I use these pretty interchangeably. The main difference is that the loss and the cost is always something we want to minimize, and sometimes the objective function we can say we want to maximize it or minimize it. Okay, so again here, this is what I just described. In order to compute the probability for a certain class y given a vector x, we first take the yth row of w, multiply that row with x. So here again, this is just writing out this inner product. Oftentimes you would see this inner product be written more like y transpose x, this kind of inner product. But since w here is already, wy dot is already a row matrix, a row vector, we don't need to write that out again, or we don't need to write the transpose. All right, so in terms of notation, we can define the sum of all these terms here, the yth row, and with our word vector x as just f sub y. And now we'll basically compute f sub c for all the other classes. And this is basically how we define the softmax function. So the probability of y given x will be the exponent of fy or f sub y divided by the sum of the exponents of fc. And we've basically already taken derivatives with respect to exponents and logs and things like that. So hopefully you can derive all the derivatives that we need here in your problem set. Okay, so let's look at this in a little more detail. So we have here basically the cross entropy error, and what we want to do ideally, just as we did with the skipgram, is we want to maximize the probability of the correct class Y. In the case of the skipgram, it was maximizing the probability that two vectors actually co-occur. In our case, it's maximized the probability of the correct class Y. And instead of maximizing the probability, we can also minimize the negative log probability. Again, the log doesn't change our argmax. And so basically, this is our main cross entropy error that we like to minimize. Are there any questions so far? I see some confused faces and some bored faces. I'm sorry for both. Do you have people who may be confused? This is, in some ways, if the prerequisite classes were a little long ago, then this might be confusing, but if you've just taken them. All right, so, and this is basically for one data point. So maybe we have one specific word vector that we want to we want to predict the probability for. Is this a location or not? In general, of course, we'll have multiple of these. So we will actually sum up our total error function or loss function will basically sum up lots of different subcases, and we'll cover more of that in the next lecture. Okay, so to give you a little bit of a background and some information theory and play around a little bit more with these concepts to familiarize yourself with them, let's look a little bit into the background of the cross entropy error. Basically, we can assume that our ground truth, and this is again some terminology here, will define the ground truth probability is basically interchangeably being used with the gold probability or the target probability as basically, again, a one-hot vector. Where we have one for the right class. So maybe you have the probability P here where you want to basically say, is this a location? This specific instance is location, no. Organization, no. It's a person. And then you say, one for person, and you basically have the number of classes is the length of that vector P. And so let's assume our computed probability from the softmax is Q. Then we can define the cross entropy error here as basically the negation of the sum over all the classes of the probability C here times the log of Q of C, where again this we computed just with the softmax function here. So it's a little bit of switch of notation here. So usually we describe P of Y given X here as P, but now since we have two, Q will be the one that we actually use, get from our softmax, and P is the ground truth probability distribution. Okay, so basically because of our one-hot P here, the only term that is left in this sum is again the negative probability of the true class, right? P of C for the thing that it's not a person, it's not a location or something, then P of C here will be 0. So we can see that this term here, the cross entropy for these two classes, is essentially exactly this one right here. And now let's play around a little bit more with this, and again we'll end up with very much the same thing. But we can basically also rewrite the cross entropy in terms of the entropy and the so-called Kullback-Leibler divergence or KL divergence between these two distributions. The Kullback-Leibler divergence is basically like a non-symmetric measure of the differences between two probability distributions. So let's look at that, and just to give you a sense of what's going on here. Basically, when we rewrite the cross entropy in terms of again the entropy and the KL divergence, we can see that because in our case here, H of P, not P, sorry, this is a typo. H of P here is 0, largely because of the definition of the entropy, which is also just the negative sum of P of C times log of P of C, where 0 of the log of 0 and the limit goes to 0. basically is this part is 0, and even if it wasn't 0, maybe eventually we don't actually have just a one-hot probability distribution that we want to predict. We may actually want to say, well, with 0.7, this is this kind of thing, and with 0.3, it's something else. So maybe eventually this won't be fully true, but even if this wasn't just a one-hot vector representation, it's basically our goal and our target distribution, so we don't really optimize for that. That's fixed and given. So if we were to optimize the KL, the cross entropy here, in either case, we'll just end up with exactly the KL divergence. And basically minimizing the cross entropy is similar to minimizing the KL divergence between the ground truth distribution and the predicted one. And just to clean that all up, basically, we can look at, so what is exactly the KL divergence? It's not a distance. Some people sort of use that terminology and say, oh, it's kind of like the distance between these two distributions. It's not a distance because it's not symmetric. But it's basically defined with this here. And now we can again see, all right, what is P of C, right? It's just 0, 1 for the correct class. And here we have Q and 1 minus Q for the only term where P of C equals 1. And hopefully, you will all see intuitively now that that ends up being exactly this again. All right, in your problem set, you'll basically derive the gradients of the cross entropy error here with respect to a matrix W and potentially also the word vectors. Which leads me actually to an interesting question, which is, what do you think are the advantages and disadvantages of training the word vectors with some other cost functions? So let's say we trained the word vectors here, and we capture these general syntactic and semantic similarities, but now we want to classify sentiment, or we want to classify that person X liked this word and person X didn't like that other word, something that is not in the original training data at all. Now, what do you think would be the advantage of not training the word vectors? Let's say we already have our word vectors, and we know, here are all the countries somewhere in that, area of the space, and here are all the words, all the adjectives and so on. And now we try to classify them with something else. And let's say in the first case, we actually do update the word vectors, and we modify them based on our task. So what would happen if that was the case, right? If I, tried to classify not just, let's say here were all the countries, but now I want to make, and maybe the countries, there's some countries here, or let's say here are all the nouns. And I tried to, okay, this is a better example. I tried to train a part of speech classifier, but I only want to tell you, 50 or so examples of different parts of speech. So now here I have all the nouns, and here I have all my verbs, right? And now if I actually have these words like run, if you look at your vector space, and again I encourage you to sort of play around with it, try to visualize what's going on, print out similarities or nearest neighbors in your space. Let's say I have here the word run, and basically I classify certain things as a noun. Now if I classify run as a noun, what will happen is it will try to, eventually the softmax will try to train a decision boundary between the two classes that it cares about. But that's just a softmax. Now, and this is kind of an interesting, something interesting that you really have to internalize and think about carefully. If we train the word vectors as well, it's not just that we train one such decision boundary, right? We also actually train where the inputs are in the original space. So maybe now I train the word vectors here, and I basically say, all right, I have run was one of my training data points, and maybe, in terms of the nouns, Seattle was another one. Now I push both of these, and if I train the word vectors, they will actually start moving such that the overall softmax has a very easy job classifying them. So maybe in the end, I update my word vectors such that they can be classified properly as nouns, and now I move them to be both somewhere over here. And I train my verbs. I pick this verb and this verb, and I push them over here with my word vector training, and now I can basically very nicely classify that these are here. This is my decision boundary. Actually, let's make it a little easier. Sorry, and say maybe training the word vectors push them to be right here. Now this is my decision boundary, and this is something that could really happen when you implement this model, and you now update your word vectors to do well on that one task. So now all my original word vectors are still here, but the few example word vectors that I've had in my training data have actually moved somewhere else because I update my word vectors to do well on a specific classification problem. Yes?
Sorry, I don't quite follow what you mean by move, like move those words. Yeah.
That's a great question. So in the very beginning, right, when we train word vectors, what we do here is we basically update them, right? So when I say move, that means originally, right? So this was what I had here before, right? Let's say this is sort of the contour levels of our objective function. And now our word vector, maybe this is our first word vector, and these are its 2 dimensions, right? We can plot this function any way we want. Usually, again, they're much higher dimensional. It'll be harder to plot. But let's say this was the position of our first word vector here. And now to optimize my function overall, I will move my word vector inside the space such that I will optimize this function. So when I say move, I basically mean exactly this update right here. I have my old word vector. Now I have some gradient, some cost function. In our case here, the cross entropy error we just talked about. And we basically push the new word vector, theta new here, or again, our word vectors here will be subparts of that general vector. We'll push them along in the space. And we move them around to be somewhere else. Does that make sense? Cool. Okay, so now maybe this looked a little messy, so I'll try to describe it again, and then hopefully you have an idea. Imagine you have a bunch of word vectors that are in this space right here, and you have a bunch of other word vectors right here. And you know right now from pre-training these word vectors with the corpus, with the script model that you'll implement, that all these are nouns, and all these are verbs. You know this, but of course a classifier wouldn't know this, right? We're not gonna, not by default. So let's say we will now tell the classifier, these guys here are indeed, these 2 are indeed nouns, and these 2 here are indeed verbs. Now, if I only trained the classifier weights, or the classifier weights, right? These are just our W here, right? If I trained only the W, it will just make this classification problem very easy. Where it basically just trains linear decision boundary, and then it will say all the things here on this side are nouns, all the things here are verbs, right? Now, what I'm asking you, what happens if I also train in my overall objective function? I basically take the derivatives with respect to not just the W, the softmax weights, but also with respect to the word vectors. Now the word vectors might move. The word vector optimization and might push all these guys here to go over here, and all these ones to go over here. So now the optimization for the softmax might end up giving me this as an objective function. So what would be the problem with doing that? Yes?
When you see new words that you haven't trained on, it's in the old word vector space.
Exactly. That is exactly the problem. Which is, if I take now my nice semantic similarity capturing word vectors, but I train them on one specific other task, and I move them elsewhere, now it doesn't really know that the old other ones, the other nouns, are basically, they haven't moved, right? They're still where they were before. It's only that I had my 2 new training samples for this class and 2 new training samples for that class. I pushed those somewhere else into the vector space. And then the softmax now has, basically would confuse it and say everything here is a noun. So it moved its decision boundary here to go over here. And now everything to the left of it will be classified as noun, including all the verbs. because after updating, my verb word vectors actually ended up down here. So basically, what we'll get here is a better fit often on the training data, right? I tell the training data, move exactly there, and you'll have a very easy time to basically classify them because you push them exactly where you want them to be. But you have a terrible, or in some cases not terrible, but worse generalization because the words moved in the vector space. So to give you an intuition of what this looks like in real life, I have here a visualization from a paper of mine from 2012 where we train word vectors to predict sentiment. So is this a positive, neutral, or negative word? It turns out when you, and this is another interesting subtlety, if you look at just the left and right context of a word, words with very different sentiment might actually get similar word vectors. So I could say, I thought this movie was really great or terrible, right? It's great and terrible might often appear in roughly similar context. So these word vectors don't often capture sentiment very well. Some of them, and with larger context size, you can do somewhat well, but by default they don't work great. So let me give you an idea of what this looks like and zoom into these word vectors here. So basically, in one, and this is again sort of similar to the PCA that we've done on the co-occurrence matrix. This is a PCA on the original semantic word vectors. In one part, we'll zoom in a second again here, but basically on the first principal component PCA, you will see that it captures mostly sentiment. So here, all we did into these word vectors is we propagated sentiment. Is this positive or negative into them using a softmax and taking derivatives of the cross-entry pair with respect to the word vectors. Now these word vectors were pushed into a different part of the space, and we color them actually by the probability of being positive or negative. So up here we have all the really positive words, and down here we have all the negative words, and in the center we'll see basically sort of neutral terms. And so when we zoom in here, basically it captures a lot of negative words. It's bland, pretentious, awful, waste, and so on. This was trained on sentiment of movie reviews, and so moving directly in your first movie review and mentioning TV is negative for this. And as we move higher up here, we basically see much more positive terms. So filmmaker, powerful, engaging, solid, hilarious, memorable, honest, terrific, intelligent, and so on. So basically, this is what happens when you train word vectors on a different subtask that isn't the general co-occurrence prediction. And that's exactly the problem now. If you wanted to now classify similar words, we would run into trouble, right? Because here we have something like TV, which is most obviously a noun phrase. We would end up being very close to neither, or jokes, or tries, or pretentious. This one is an adjective, this is a noun, this is a verb. So training on the sentiment subtask basically changed the entire semantics of this word vector space. All right. With that, I want to conclude. Basically, so far we've learned how to train word vectors, and we've had a first introduction to how to classify single word vectors. Of course, that's something we rarely ever want to do. In most cases, we want to classify a word in some context. So in the next class, we'll actually look at classifying entire windows, and then we can really see in this context, this word has that specific class or meaning. And we've covered the softmax classification and its cross-entropy error. In the next class, we'll actually use a much more commonly used error function, which is the max margin loss. Thanks.